Hello guys, sorry for the late post. Today I'll be doing a video on the mechanics quiz. Um, Now probably nobody's gonna watch this today, obviously, but maybe you could think of this as like a study for you, just before you enter the exam. This is for grade 10, specifically Al-Batin. Uh, so yeah, let's begin. Okay, so the figure below shows a homogeneous block of mass M placed on four identical, equally spaced springs of constant K each. So the block is in equilibrium here. The expression for the compression of each spring. Okay, so let's see, right? This block is on the springs, right? Now there's a few things we should know here. Let's see. Now in any spring, the force of a spring is equal to constant K multiplied by the compression. And now look, there's four springs, right? There's 1, 2, 3, 4. And that means when there's four springs, that means we have to multiply like the effort required to also including the fact that the block exerts a force with the mass. We don't know what the mass is, but we know that F is equal to mg, the W is equal to mg, W is equal to mg. So, we need four. They said that this block is in equilibrium, and that means that these springs had to exert this amount of force to keep up this weight. You have to think of it like this. These three springs, each one produced K delta L, K delta L, K delta L, and all of these added up. All together, they work together, so then they can control mg. And that's why we equate them, because they said that it's in equilibrium, meaning that all of these add up and it's just enough to equilibriumize or whatever the block. Okay, so now we have 4k delta L mg. Now remember, delta L is the compression. Okay, so we have compression here. And now we'll just isolate compression. So we'll move everything to the other side. We'll move k and 4 to the other side. And we'll thus get delta L is equal to mg over 4k. Easy enough. So the answer is mg over 4k. Okay. Moving on. Let's see what we have here. Okay, now over here we have a free body diagram. Let me just quickly put this on a Samsung Notes. Just give me a second. Okay, so I've just cropped this on over here, and we have the required to find over here. Let's read the question properly just before we get into this. So we have the body diagram here. They gave us a few things, not three. Let's see here. They first gave us the inclination of the slope made with the normal. Sorry, made with the horizontal, which is 37 degrees. They gave us the weight of the block, which is 4.7 newtons, and the tension of the string right here. However, I'll show you why the tension is not going to be really relevant for now. This is a super easy question, and they try to complicate you in this stuff. When they ask you for the normal reaction of the magnitude of the normal reaction, they are looking for this here, n. Now, to get n, let's first look here, right? We have n. N is always perpendicular to the block in general. So we can assume that the axis in which the normal force is in will be now our y-axis. And perpendicular to that is obviously the x-axis. Sorry, let me just open it out more. This is our x-axis. Now, over here, what we notice here is that we have the weight. They give us here the weight, which is 4.7. So that means over here we can say that W is equal to 4.7. Let me just make the thing smaller. This is good. So we know that the weight is 4.7. However, we want to find a way to get the normal in terms of weight, with just weight, because the tension won't really help us, given that over here it's nowhere around the y-axis. Now look, we'll just apply trigonometry over here. We have the weight, and so we have the weight here, 4.7 newtons, right? We'll treat this like normal trigonometry, right? And you know how force doesn't normally have a length or specific direction. So we'll just, I don't know, let's say we have the weight here. We'll just quickly put it down like this. We'll stop here. And now this over here is supposedly 4.7 newtons. Now, we have this 37 degrees here, and we know that this weight is perpendicular, like when you pull down the arrow of the weight, it is perpendicular to this bottom over here, the horizontal. So, now with this perpendicular thing, and also given that over here is also perpendicular, we'll do, and also over here is perpendicular. Now, we can do similar triangles here. If this is 37 degrees over here, that means over here, sorry, let me just remove that. Over here is also 37 degrees. So now look, now we have a new triangle here. 37 degrees. We have our weight here, which is 4.7 newtons. So let me just take this triangle that I've circled right now. And we have something like this. This is just part of the y-axis. As you can see here, you see this is the y-axis here. This is 4.7 newtons, which is the weight. And now we have other components that we're looking at here. We have here y-axis. Y-axis mainly is supposed to represent the magnitude of n. Now why not simply n? Because it's facing downwards, so it's just going to be negative n. But we just want to look for the magnitude of n right now. You see over here they're asking for magnitude. So in order to do this, we'll do simple trigonometry. We'll just do 4.7 cosine 37 to get the magnitude of normal. So 4.7 cosine 37 is 3.8 approximately. 3.8 newtons. So now we have the normal, 3.8 newtons. Moving on. Now, most of the questions are relatively easy, I'd say. Now this one over here. When they say non-inertial frame of reference, they mean here that over here, A is greater or A is not equal to 0, sorry. A is not equal to 0, meaning that it is accelerating and it is not really going in uniform motion. Now, what can be considered in uniform motion? A stationary car means that A is equal to 0. That means it's just staying in one spot. V is equal to 0. Everything is equal to 0. Now, it's just uniform, not moving. So that means this thing is an inertial frame of reference, and that means the stationary car cannot be considered an option. So we'll cross that out. Okay, let me just do a full screen here this time. Okay, so now, we already said the stationary car is wrong. The floor of a playground here, it's just the floor, right? Nothing's gonna really affect it. And, you don't always feel the floor moving beneath you. I mean, the earth does move, but that's different because the floor beneath you doesn't move. The floor doesn't shift or anything. Otherwise, we'd be falling constantly if you were to stand on the floor. So, no. The velocity on the floor is also 0, and the acceleration on it is 0. Here, velocity was 0, acceleration 0. Now, what is mainly important is that acceleration only must be 0. So I'm just saying v is equal to 0, but v is equal to 0, that means it's at rest, and when it's at rest, that means a is equal to 0. Here is the same case, v equals 0, a equals 0. Uniform rectilinear motion means that a is equal to 0, but v is constant. Okay. And the final one is just a rotating wheel. Now, they might think that all of it is wrong because now over here they've given no description here. If they don't give a description and all of these seem wrong, except this one, we don't know what this rotating wheel is. Many vectors can affect it. Air resistance, any object on it possibly. They didn't say if it's uniform or not. All of these are proven to be not uniform, except the rotating wheel. So we must only pick the rotating wheel as a non-inertial frame of reference. So just remember, non-inertial frame of reference is constant acceleration. No, non-inertial, it means not non-constant acceleration. Zero acceleration. And inertial frame of reference means acceleration is equal to 0. Okay, now based on Newton's second law of motion, the blank acting on a body. Okay, now we should know simply the second law, Newton's second law of motion is simply just F equals to ma, where m represents the inertial mass, A represents acceleration, and F represents force. Okay, so that means we can simply say the net force acting on a body is proportional to the product. So product, that means we already said F is equal to M multiplied by A. This is over here is a product. M is multiplied by A. Now, when they say inertial here, that means after that always comes mass, and product of its acceleration by its inertial mass. Now I can't really fit the word acceleration into that slot. So here that makes sense, right? Net force is equal to the product of, or directly, or just proportional to the acceleration by its inertial mass multiplied. Okay, easy enough. Moving on. When an object M. Okay, now this is Newton's third law. In Newton's third law cases, like let's say there's only two objects interacting, meaning that we cannot draw a free body diagram. Since that, in a free body diagram, when there's like particles or like objects or anything, they cannot be exerting a force. Only forces are exerted on it. So let's see here. Let's say, I don't know, object M exerts a force with F1, right? And now, look, when there's a force exerted on a body, the body that has experienced this force will exert an opposite but equal force. When they say opposite, they means opposite direction but equal magnitude. Thus, that means that the magnitude of F1 is equal to the magnitude of F2, but opposite direction. That's that. This is the third law. Okay, so magnitude is equal, F1 is equal to F2 in magnitude, and they are both in opposite direction. So question 7, question 6. Now this one, I swear to God, they're here, they're just messing with you. Read the question before you do anything, really. They're just asking you here the inertial mass of the block. Just remember, look, mass of a block is just conserved all the time, right? It never changes in any case. Only the weight does, depending on the environment or the planet that it's on or whatever. But the mass never changes. So you have to say the inertial mass of the block is equal to the gravitational mass of the block. So that's equal. Now, some people already in my class asked me to solve this because they don't understand this, but it's actually a lot easier than it looks. So let's see here. First, we'll draw a body diagram here. Let's see. So they said here that there's a 1,500 kilogram car is held in place by a light cable on a frictionless ramp. So we have a ramp. They said that this ramp, it makes it 10 degrees above the horizontal. So horizontal is always the very lowest, and it's obviously horizontal. And on this ramp, there is a 1,500 kilogram car. We'll just denote this as a particle here. Let's see what the force is acting upon it. Now, before anything, they gave us a mass. They said it's frictionless, and it is held in place. When it is held in place, that means we need to know that it is in rest, and that means the following: that the sum of x forces is equal to 0, and the sum of y forces is also equal to 0. You should know these two. So let's see here. We have the block here. Sorry, the car here. What's acting upon it is obviously first the weight. We'll focus on the weight here. I'll write the weight out here. They said over here it's 10 degrees. However, that there's a light cable on a frictionless that's holding this car with an angle of 25 degrees along the line of greatest slope. Now, when they didn't really say that, but what I mean is it's making 25 degrees with, the ramp. So here, now we have the angle measures. Now I haven't written all of the applicational forces that are acting on this. So we have the weight and we have the normal. What we also have is this tension here made by the string. Okay, this is good enough. And also the fact that this here is perpendicular. Okay, perfect. Now we are ready to or almost ready to anything that they asked us to solve actually. First one here, they're asking for the tension in the cable. Now, look, there is one easy way to do this, and that's by, let's first see what forces we can easily achieve. The easiest one to achieve is weight. Weight is equal to mg, simply. So let's see here. Mg is equal to 1,500 kilograms multiplied by 10, because g is equal to 10 meters per second squared. So thus 15,000 kilograms, 15,000 newtons is the weight. So now that we know the weight, normally we're not gonna have this question yet, or probably not at all, but we should know that on a horizontal surface, that the weight is equal to the normal on horizontal slope. Now, in the case when the slope is slanted instead of being horizontal, what happens is weight is no longer equal to normal directly. Instead, the magnitude of the normal is equal to the weight of the normal multiplied by the cosine of the inclination. I'll explain how it works right now actually. Okay, so we have the weight here. Let's look at the weight here. I'll change the font of the marker to, let's say this color is good. Okay, so let's look. So first we'll draw axes, right? Drawing axes, feels the most appropriate for this situation. It's not perfect at all though. It's really not perfect, but whatever. We have y and we have our x-axis. So we have our y and x-axis here, and we have this force here, W, making, we don't know how much degrees with anything yet, but what we can do here is we can take this here is right, this here is also right, and using the theorem of similar triangles, we can get that this angle here is 10 degrees. Easy, right? So now that we have here is 10 degrees, let me just erase that right angle there. Sorry. Give me 1 second. Okay. So now that we have here is 10 degrees, we can get two components here. We can get either this component here, which is equal to the magnitude of this normal over here. It's just going to be negative because it's pointed downward. So here we have an n, which we want to get. In order to get this, we have weight, we have 10. Now we'll just apply simple trigonometry. We have this triangle here. Let's redraw this triangle. Okay, so over here it will be 10 degrees. Here it will be right, and the other angle doesn't matter. So we have over here the weight here. We have the normal force here. It's not really equal to the normal force, yes, equal in magnitude, but no in terms of actual values. So the magnitude here is equal to the magnitude of this here. And now we just want to get simply the magnitude of the normal here. Wait, this is solving the other question. Sorry, just give me 1 second. I did a mistake, sorry. I accidentally solved this one before this one. Ignore, sorry. I'm not gonna restart this video because this already took a while. So just bear with me. Instead, I was actually meant to find the horizontal component over here instead. But look, no, actually, let's continue. We have here this weight, and over here, as you can see here, is the horizontal component. Or sorry, no. X component of W. Now, to be honest, the X component of W, it doesn't, as long as it's pointing, as long as you can acquire it through this, you can state the following. W sine 10 is equal to the X component of W. Now over here, it doesn't really make sense on how you get the like how this can immediately be the x component. There's a better way to do it, and that's by, or something like better, like for you to understand easier. And that's by, how like force, first of all, force, it doesn't really have a distance. You see, like this can be represents 5 newtons, this can also be represented 5 newtons. So it doesn't really matter. So we can say, we can easily say, let me draw the x component first of the weight. I'll draw it in yellow here. This will be, denote it as WX. Now what I'll do here is I'll draw here up until here a right triangle here, just so that this is right, and if through similar triangles I get the fact that here is 10 degrees. Let me get this out of the way. Here is 10 degrees. And with this, I can do another simple rule here. Over here is WX, over here is W, and over here is 10. Thus, W sine 10 is equal to WX. Now, I'll show you why it's important to get WX. So, you already know that W here is equal to 15,000. So, on the calculator, if we do 15,000 sine 10, I was about to do cosine 10, it's sine 10, and you get, so that means over here WX is equal to 15,000 sine 10, which is equal to 2,604.7. Over here, this is the answer here for WX. Okay, now we have one direction, and now we have to get the other direction here. Now over here, we'll just call this the x component of t. Super easy to get. We just have to do t t cosine 25 is equal to the t component of x. So now, having the w component of x and the t component of x, we can say here that the sum of all x forces is equal to t cosine x, t cosine 25, sorry, plus, and then we have wx, which is, in this case here, 2,000. We can just write this. Let's just write this. This is way easier and way more exact. And now, we were already given that here it's equal to 0. So, I equated it to 0. Now, our goal is to find tension. So, we'll find this here, value here. So, that's T, the magnitude of T, is equal to, now you might get a negative number, yes. But if you get a negative number, you'll have to cancel it out. Since they definitely just want the magnitude here. Or more likely, I was meant to put here, you can also put minus. That also works. But plus is better, and then you can just ignore the negative, whatever you like, as long as you finally get this answer here. You get 2,874 newtons as a whole integer. Basically, the value is 2,874. It's 2,873.99, but that's very close and approximate to 2,874. So now, oh my god, I erased it. Give me 1 second. Okay, so I quickly just drew a quick sketch, and I'll just draw the axes again. Here's the y-axis, and here's the x-axis. Okay, so now they want to this time to get the normal reaction. So they want n now. What is n? They don't know. To get n, this time now we must use Fy, the sum of y forces is equal to 0. Now, what are the following y forces that are applied here? Let's see here. So we know that this angle measured over here is 10 degrees, using the theorem of similar triangles here. Over here is right angle, over here is right angle, over here is 10, over here is 10, thus, and this angle here is also right. Thus, this over here is also 10 over here. This is 10. Okay. So we have W and we have 10 degrees and we want to find Y, but in this case Y over here we want to find the magnitude of N. So to do this we must do W cosine, not sine but cosine, 10 is equal to the magnitude of the normal. Now look. So let's see here. This here, this is just the magnitude of the normal, right? Magnitude of the normal, okay. So we have W cosine 10. So we have W here is already equal to 15,000. So if you to write this here again as 15,000, actually we'll keep it like this, cosine 10. 15,000 cosine 10 is equal to this. Now they said normal reaction of the support acting on the car. So when they say the normal reaction, this is just the normal force applied by the car. Not by the car, just on the car. But what is also applying, like that is kind of disrupting this normal, is the tension here. This tension here, it also applies a Y force. We'll call this Y force here in yellow. Here we'll call this Ty. Ty is equal to T sine 25. And we should know that over here, we must do this minus this to get, so let's see, wait. So that means you must do this minus this to see, think of it like how much is how much is like as a deficit, like how much do you need to compensate for however much, like in terms of normal reaction. When they say normal reaction, they mean Y. I'll show you what I mean, right? We got the sum of Fy forces, right? We already have tension, which is 2874. So we will rewrite this quickly. Here, the value of this here is let me write this. So I simplified it, I got 14772 point, no, that's it. And then minus 2874 sine 25 is equal to the sum of Y forces, which is equal to 0. Wait. Sorry. No, wait. For it to be 0, wait, no. Okay, this isn't actually the sum of Y forces. This is just partly the sum of Y forces. Once we have this, we must also add, finally, the normal force, which then makes this the sum of Y forces, which then makes this equal to 0. So that means here, plus n equals 0. We calculate, we get 14772 minus 274 sine 25. Now over here, I will rewrite this, sorry. I was supposed to put multiply by minus, so instead it's supposed to be written like this. Minus 14772 minus 2874 sine 25 is equal to 0. Thus, n is equal to 14772 minus 2874 sine 25. Deducing it with this, we get that the normal force is equal to 13557 newtons to the nearest integer. Finally, this is already the hardest question. Now we can simply and easily move on. Oh, okay. Oh, this one here. This is easier, though, which is good. Here is easier, so that's good. Let's look at the other information that we already given. They gave us that the gravity acting on the load is, the gravity is 519 newtons, and the rest of it is already shown on the diagram. Let me just quickly make a sketch. Okay, so, easy enough, that's all we need. if you didn't read the question, sorry, they also stated that it was in equilibrium. This thing is in equilibrium. When it's in equilibrium, we need to know two things, and we're just going to apply this again. All y forces must be equal to 0, all x forces must be equal to 0. So let's see. First we're gonna follow the order of the questions. We'll start with finding AC. We'll denote this as alpha, and we'll denote BC as beta. So here we have beta and alpha. Okay, so we're gonna find alpha first. Let's first draw an y-axis for ourselves. Sorry. And then we have a force, which is weight. This weight is 519 newtons. And over here alpha, this angle measure, if over here is 90, that means over here is 30 degrees. So that means what are the only components we have? We only have one y component. So that means what we must be using is this one over here. So let's see. To get the y component of alpha, we must do alpha cosine 30. Because you see over here, if you flip it and then you see here, this line that right now I'm going to outline on red is adjacent. So that means when it's adjacent, we apply cosine. Okay, so alpha cosine 30 is plus, and then W force is equal to which is equal to Fy, which is equal to 0. Now they already gave us this, which is 519. So now that we have this here, is equal to 0, then we can say alpha, or the absolute value of alpha. When they say tension and they don't need anything else, they're obviously asking for the absolute value of the tension. So 519 over cosine 30. Now here's one thing that they do that's kind of stupid in my opinion. They say that the answer on the calculator, they say it's 599.3. Now, when they ask for the nearest integer, it really should be 599. But the answer is 600, so we'll just keep it that way. It is, but it is, not gonna lie, very relatively close to 600. But the real nearest integer is 599. I don't know why they're doing this. Okay. I went out of the screen again. It's fine. Easy peasy. We'll regenerate. That sounds weird. I don't know. Here. Is equal to 600 newtons here. We just got this. And now we're trying to find beta here, which is BC. Now we'll keep this imaginary line here. Which was our y-axis. And now let me just draw the rest of our x-axis. So now here, to get this time, last time they said it was in equilibrium, and we used already Fy is equal to 0. We use this, but we have not used Fx equal to 0, so we must use this. Well, let's find all x components. Our first x component is beta. So beta plus, and then we must find the x component of alpha. To find the x component of alpha, how do we do this? We have 60 degrees here. Now, you could do two things. We have 30 degrees here. We need to find this line over here. So over here, we just do 600. We can do 600 sine 30 or 600 cosine 60. Both work, since over here is 60 degrees. Got this? Okay. Okay, so I'll prefer 600 sine 30. So beta plus 600 sine 30 is equal to 0. Now, easy. Now I find the magnitude of beta, which is equal to 600 sine 30, which is finally equal to 600 multiplied by half, which is equal to 300. Thus the answer here is 300. Now everything else is easy. Let's see here. Yeah, easy peasy. Directional force. They said that this ball was thrown over here, meaning that the ball exerts a force onto the right, which is on the wall. And then this is Newton's third law. If there's a force exerted here, there was a force exerted here. Equal magnitude, opposite direction. Over here, we should know here, that F is equal to ma. That means that Newton is equal to, as in newtons, like the unit, kilogram multiplied by m over s squared. So we'll rewrite this as n is equal to kg multiplied by m over s squared. And n as in like just one n. So now we can finally pick this as our answer. Okay, so Newton's, now when they say there's no formula involved, when there's no opposite or magnitude and the opposite or equal direction magnitude, if they don't involve these words, or they don't involve something to do with force, acceleration, and mass having a relation, then they're talking about the first Newton's law. And it states that any object continues in its uniform motion, meaning that velocity is constant or it's in rest. Now when they say, we just say state of rest or uniform motion, unless it is compelled to change that state by an unbalanced force or by an accelerating motion. So let's see here, or just simply by forces. They don't describe the forces. It's normally unbalanced forces. So yeah, and this causes like deviation inside the acceleration. This is super easy. This is literally like somebody who doesn't even take an ounce of physics can get this. Physical quantity that changes as the force acts. So obviously mass is wrong. Mass stays constant in all cases. Velocity is the only thing that changes really. However, volume, it doesn't change, and power, it also doesn't change. It's only velocity. Simple. Okay. Over here, F is equal to ma. This is just a formula we must remember. When unbalanced forces act on an object, then the sum of forces is non-zero, because assuming that that object is on rest or in uniform motion, and then suddenly an unbalanced. When they say unbalanced, that means automatically the sum of forces is non-zero. Because it was initially in equilibrium, now it's no longer not. Now it no longer is. Wrong grammar, sorry. Okay, now this is super easy. We have just, actually I'll just do it like this. Here. We have a particle. We have a particle here. As an object, I mean. 10 newtons north. And 10 newtons south. Sorry, and 15 newtons south. Now this is simple. We must just do 15 minus 10, which is 5. And since the greater force is over here, it's in the south, so it's due south. 5 newtons due south. Okay, now here, it's so simple here. When they say inertial mass, now guys, remember, when we said that the inertial mass is equal to gravitational mass. I'll show you when we'll apply this later. Whatever, gravitational mass. Okay, so here, they already say here it's A is equal to 3 meters per second squared. And mass, they didn't specify the mass. However, actually, wait, no, this is irrelevant. Sorry. Simply we just do F net is equal to mass times acceleration. We have acceleration, we have F net, which is 90. So we have 90 is equal to 3m. Thus, 90 over 3 is equal to 30. 30 what? Kilograms. The options here are tricky. Anything that has a unit and then kg after, wrong. Literally, you don't even have to calculate. There's only one correct answer here. Okay, here we just did this. Here you go. Yes. It's the same as saying mass. It's the same as saying mass times acceleration. Meter per second squared, and kilogram. Yeah. A constant force produces, let's see, zero acceleration. The acceleration produced by an unbalanced force is, now when there's two unbalanced forces acting upon each other, they do eventually, look, the acceleration produced by an unbalanced force, or simply by any force, you should understand that force is always directly proportional to acceleration. So it is directly proportional. However, mass is inversely proportional to acceleration, or vice versa. So that means the acceleration produced by an unbalanced force is inversely proportional to the inertial mass of the accelerating object. Here, we should know some rule. I don't remember the name of the rule, but normally when you're mentioning the Newton's third law, first you have to denote force as F in all cases, and then when there's two labeled objects, like for example the woman is object W and the cabinet is object C. So you see the woman is exerting a force on C, so we can say W, no, there's force starting by the woman going over here, force WC. You can write, normally I like to write it like this, W dash C or W slash C, and you get the force applied by the woman on the cabinet. And normally, and not normally, just all the time, in Newton's third law it states that therefore the reaction is opposite but equal in magnitude. So we were still write F, but instead of woman on cabinet, now it's cabinet on woman, because you see equal in magnitude. So this is how we should write it here. What you can also write it like this. I'm pretty sure, but this is my favorite. I don't know. So F, this is when the cabinet is on, because you see the arrow is pointed, you see how the arrow is pointed, it's pointing over there, on the woman. So it's cabinet on, oh, what's happening? Oh, woman, and over here is force, woman on cabinet, because the arrow is pointing from the woman to the cabinet. Easy. 2 questions and none of them are even, okay, and none of them are even calculation, I'm pretty sure. So which law states that there's action-reaction forces equal in magnitude, opposite in direction? This is the third law. Okay, so the illustration below shows 2 skateboarders A and B pushing each other away. Now, by simplicity, we should know that these two are 100% wrong. This guy, he exerts the force on this one, and he exerts the force on this one. They both drift away. We just know that as a simple fact. So these two are definitely wrong. The two forces have the same magnitude. No, look. We don't know who pushed first, okay? Maybe they're assuming that action is A and reaction is B. Maybe they don't mean it. I don't know. Look, one of them push each other away. What happens when someone pushes away? There's F, A, B, A on B, going this direction. Therefore, there is over here F B on A, equal in magnitude. These are equal in magnitude, so that means the two forces have the same magnitude. The two forces are opposite in direction, yes, because they're both pushing each other. Opposite in direction, therefore. The two forces have different magnitudes. This is wrong. Yeah, because we already said that they have the same magnitude. No. It's not different magnitude. It's the same magnitude. So these two are the only answers. Yes, that's it. So I'm hoping for full. No? Oh. Oh, just give me a second. Okay, wait. First I'll fix 18 because I'm pretty sure I just missed like one small number in 7. I still did the correct method. There's nothing that's different here. Over here, I was supposed to put over here reduces constant acceleration. Sorry, yeah. Yeah, everything else is correct. Here I don't see what's wrong. We compare the answers, it's definitely the same. Watch. Look, here is the same, just by one number. I must have made a mistake while putting the numbers. It's fine. I should have put the exact values. Just don't do the same mistake as me. Keep the values exact. It's the same exact thing. Okay, well that's it. Thank you for watching the video. Speed this up and get to the questions that you need help in. I hope this helped you. Thank you.